Welcome to the introductory video about electric fields. Our next topic is as we look at electrostatics. So if you look in chapter 24 of your book, there are some sections here that you can see I've clicked on that are about electric fields. An electric field, similar to a gravitational field, is an area of influence. So it's an area where something with a charge will feel a force, and that is caused by Coulomb's law, like we've already talked about, that like charges repel and unlike charges attract. Well, if you have a charge and you move a charge anywhere near it, it's going to influence it. So we have this construct that we call a field, which is an area where something can be influenced by it. And if you look in the section about electric fields, they talk about this: charged object, nature of electric force. Okay, so fields are they're not an actual physical thing, but they're an area of influence. And what we do is we look at things like what are called electric field lines. And here's a short little video that shows you an actual experiment where they're showing and demonstrating how some electric field lines with some oil and such.
It is a liquid which has a high insulation properties, semolina seeds that polarize under the action of electric fields and hence orientate along the electric field lines, and then switch on the power supply to about 3 kilovolts. Then semolina seeds are sprinkled into the oil, and as the atoms inside these semolina seeds become polarized, they will move around and orientate along the electric field lines, thus revealing a pattern. In this case, we are simulating the electric field lines between two charges. Now two different electrodes are placed in oil to simulate the electric field pattern given by an isolated charge. So one is a pointed electrode and the other one is a circular electrode, and both are connected to the positive and negative polarity of the supply. Semolina seeds are sprinkled onto the oil. Time reveals the electric field pattern. We use two elongated electrodes, semolina seeds sprinkled onto the oil. Some time is allowed and the pattern starts to become visible.
Alright, now we can simulate those same electric field lines here if I put out a charge and I then choose to show the E field. You can see it's coming all out radial like they showed you there, like they showed you in the thing. If I have two unlike charges, you can see the field lines start bending. These arrows show the direction that a charged object would feel a force. Now, what type of charged object? Because a negative object and a positive object will feel opposite forces. By convention, which just means we all decided together, the test object is a positive test charge. So if I put a positive test charge right here, right on this, it would feel a force in the direction of this red arrow. As I increase the amount of charge in any given area, you can see these lines get more and more defined. They get stronger and stronger. And if I put sensors, these are E-field sensors, notice as I move that around, that positive test charge, it's always in the direction of those arrows. And as I get closer, it feels more and more force. And then as I get out here, it's weaker and weaker, but it's always in these direction of these arrows. These are called, and if I map these together, these are what are called field lines, which is what you saw in the demonstration. I think a great way to visualize these, one is called a plasma ball, and another great way is with the Van de Graaff generator. So here's a clip from Bill Nye where he's explaining how a Van de Graaff generator works and demonstrating a little bit in Bill Nye style.
Bill Nye the Science Guy. Bill Nye the Science Guy. Bill Nye the Science Guy.
Now suppose we want to make a big static electrical charge. Well, we could use something like this. This is called a Van de Graaff generator. It's named after Robert Van de Graaff. So here's what happens. Electrical charges are deposited on this rubber belt. The rubber belt turns and redeposits the electrical charges up here on this metal ball. Now, since this next part of the demonstration rocks, I'm gonna put on my rocker wig of science. Yeah. Now, start the rubber belt turning. Electrical charges are being deposited on the metal ball. They're running through my arm and being deposited in me. And look, it's building up in my rocker wig of science. See, since these charges are all the same, they're not attracting. No, they're repelling. They're pushing apart. So they're pushing the hairs of my rocker wig apart. Now, if I could find a way to get these electrical charges off of me back into some other parts of the room, the hairs wouldn't repel each other. There wouldn't be a static electrical charge. No, the charge would jump. So let's try it. Watch what happens when I bring this ball near this ball. See the spark? The charges jumped. The static electrical charges aren't static. No, they jumped. Static electricity. It rocks. See that? It sparked.
Bill Nye the Science Guy.
And let's go with one final demonstration. And it's about plasma and what happens to plasma in a flame when you put it in a field, since the plasma is made up of ions. And so here is further proof that not only is there an electric field, but that the plasma is made of ions.
What is a candle flame really made of? I'm at the Palace of Discovery in Paris to do an experiment that beautifully demonstrates the answer.
Ce conducteur-là sera chargé négativement, d'accord? Par ce phénomène qu'on appelle l'influence électrique, celui-ci sera chargé plus.
Okay, so we're turning on an electric field here. You can see that the flame is spreading
Yeah.
out. Quel est le voltage ici?
Il doit être à peu près 20 000.
20 000.
On voit bien que t'es papillon ou non? Oui?
Papillon?
Papillon, ça fait comme
Oui,
ça.
oui, oui.
Comme un papillon.
Oui. That's very cute. It's like a butterfly.
Alors la flamme, c'est un plasma. C'est un milieu totalement ionisé.
And you can see that the flame has two separate pieces to it now. One is going towards the negative plate, and those would be the positive ions, and the negative ions will be going towards a positively charged plate. So we see the flame kind of flattening out.
All right, so there's everything about electric fields that we're going to talk about today. Thank you.